Hello, everyone. How are you all doing? Good? Maybe, who knows? We're here. Okay, so welcome. I'm just gonna give you a heads up. I have my kids covered every single day except for this one session on Thursday. That is my husband's responsibility. And he totally flaked on the very first one. So I do have my 4-month-old daughter sitting next to me. She's a really good baby, but if you see me looking over there or putting the mute on, it's because we're at like DEFCON 1 with her, okay? So just know it's not you, it's me. No, it's not even me, it's my husband, but it is what it is, okay? So let's get started with some chemistry. I'll share my screen with y'all. Share screen. Cool. Okay, and some of these slides are like, I feel like they're pretty old school. I might try and do a little bit of looking around and seeing if there's maybe some more updated slides, because some of the like links and stuff on these aren't not taking me anywhere. So I may switch slides up next time. Yeah. Sleep. Okay, so we talked about physical changes and chemical changes last time, which sort of ties into or goes along with physical and chemical properties, right? So a physical change is any time that matter makes some sort of visual change, mass change, volume, temperature change, but the composition of the material doesn't itself change. So if I take silver and I heat it from 44 degrees Celsius to 48 degrees Celsius, it's still made up of the same material. Chemical changes, on the other hand, are when you're going to get a new substance. So anytime you write it, you can write a chemical reaction for it, that's going to be a chemical change. So if I take methane and I combine it with oxygen and then I get energy, CO2 and H2O, we would say that it's an example of combustion, and we would say that's a chemical change. So here is sort of a real life example of a chemical reaction. So what we have is hydrogen gas, H2 combining with oxygen gas, which is O2. We can see that these things are separate from each other, right? They're in two separate containers. They're not having interactions with each other, and they're definitely not combined or fused together. When we burn it, it will undergo a chemical process, and we can actually form water vapor on the other end. So we'll get a flame and we get water vapor. So here, now we can see that, you know, one of those little oxygens has now stuck to two of the little hydrogens. So what is at the end of this reaction is different than the two things from the beginning. When we write out a chemical reaction, which we'll get to practice a bunch later on, the little arrow that separates your reactants from your products, this is where the chemical reaction is taking place. I'll skip over this slide. No, I don't want to do that. Hold on one second. Skip that. Okay, so when we were talking about the different types of matter back, let's just go back there, why not? Here, we were talking about things that are mixtures. So we have a heterogeneous mixture and we have a homogeneous mixture. In a heterogeneous mixture, hetero, the root there meaning that it's different. So a heterogeneous mixture would be something like bananas and oatmeal. A homogeneous mixture, on the other hand, are two things that are mixed together, but they're evenly mixed. So homo being the same. So we would think of a homogeneous mixture or a homogeneous mixture as salt water. The thing that's different about mixtures, these two guys here versus say like a compound, is that I can change the proportions in my mixtures, right? I can make my water extra salty. I can make it just a little salty. I can put 2 bananas in my oatmeal instead of 1 banana in my oatmeal. When I'm dealing with a compound, like for instance, carbon dioxide, CO2, I have to have 1 carbon for every 2 oxygens. That's just the way it is. That's the recipe for it, okay? So when looking at mixtures, because the materials in there aren't chemically bonded to each other, like in salt water, there are different ways that we can separate mixtures out from each other. Oh yeah, sorry, we kind of already went over this, but a compound, remember that a compound can be broken into simpler things. Okay, so separations of mixtures. So a couple different ways we can separate mixtures. One is through a process called distillation. So over here, I've got a flask filled with salt water, and I want to purify or distill the water. So what we will do is we'll heat this thing up. What ends up evaporating is water, and what will be left behind in that boiling flask at the end of it will be the salt, whatever it is, sodium chloride. I run it through a condenser tube that sometimes will have cold water passing through it to condense it. Sometimes it can condense just with the temperature of the room. And then what we get is a receiving flask over here where we have pure water. So this right here is a pretty simple setup. It is very energy intensive though. So, you know, you've got to run that Bunsen burner for quite a while. We know that water has a heat capacity of 4.18, which is a really, really high heat capacity, meaning that it takes a lot of energy to heat it up. So this is one reason why when we talk about like water shortages and things like that, desalinization is not necessarily the answer to water shortages, because if we want to heat up all that salt water and get fresh water to drink, well, we've got to use a lot of fossil fuels. So the only places that are really practically doing distillation like this for fresh water are places in the Middle East where they have an excessive amount of fossil fuels. Just FYI. All right, another way is filtration. In filtration, if there's a solid substance that happens to be mixed in with a liquid substance, we can drain it out. So I have no idea what this orange stuff is, but there's some sort of orange goop sitting in a clear liquid. When we run it through this funnel, the filter paper will capture the orange goop and it allows the clear liquid to collect at the bottom. Chromatography, this technique separates substances on the basis of differences in solubility. So some things are soluble, and when I say soluble, I mean, sorry about that. I mean that they can dissolve in the material. So salt, for instance, can dissolve in water. But something like silver chloride won't dissolve in water. So we can use a variety of different solvents to purify out our material. All right, so units of measurements that we are going to have here in chemistry this semester. So we are going to be getting comfortable with the SI units, which is different than what we have every day. We tend to use the British system, which makes no sense. So we've got inches and feet and pounds and gallons and quarts and all these things that have their own way of structuring and cutting units down, and it can get a little crazy. So, you know, you maybe find it easy to figure out how many inches are in a foot. There's 12 inches in a foot, but it's like how many feet are in a mile? I don't remember, 5,000 something. It's these random numbers that don't work with each other. The SI units, on the other hand, are all on a base of 10. So if you want to go to a bigger unit, you just would multiply by 10. If you want to go to a smaller unit, you can divide by 10 step by step. So that's why we really like these. So for mass, the SI unit for that is a kilogram. Kilo is a prefix, and we'll talk about what that represents. Gram is the base there. Length is going to be in a meter. If you've never worked with a meter before, it's close to a yard. And it's like, well, what's a yard? 3 feet, because that's just what they picked, okay? So we're gonna try and move away from some of those weirder numbers into just base 10 where we can do hopping with decimals. Seconds is for time. Temperature is in Kelvin. Kelvin is gonna be related off of degrees Celsius, all right? Kelvin is whatever your Celsius temperature is plus 273. And we'll go into that a little bit more, but it's just a better way to work with numbers as far as temperature in equations, because Kelvin doesn't have a zero value or a negative value. Okay, the smallest Kelvin you can have is 0, which is classified as absolute 0, and we don't ever really get there. We just sort of like asymptotically approach it, because at absolute 0, all particles would stop moving. So we'll get into that later. The amount of a substance is based off of a mole. So again, a mole is something that we'll expand on a little bit later in the semester. We're not going to do anything with electric current and luminosity for now, so we'll leave those. Okay, so here are all the prefixes, and I'm gonna turn the annotate on. The annotate button through Zoom makes it look like I mean, I have the handwriting of like a 12-year-old boy, but it's gonna make it look like I'm a 2-year-old boy, so just bear with me. But so we've got, right here we've got deci, centi, milli, kilo, mega, giga. So I'm gonna put right in here. This is gonna be where our base unit sits. So you can have a couple different things for your base unit depending on what you're talking about. So some examples of base units would be gram, second, Kelvin, we don't really use a whole lot, liter, let's see what else, meter, okay, all those things that we were sort of talking about prior can be a base unit. And then if we want to get a bigger unit or a smaller unit, we can just stick one of these prefixes on there. So you are going to need to know, I'm going to say kilo, deci, centi, milli, micro, and nano, okay? Here is their meaning. So my base unit, again, is stuck somewhere in here. So let's say we have the meter in M. A gigameter is 10 to the 9th times bigger than a meter. Right. A kilometer or a kilometer is 10 to the 3rd or 1,000 times bigger than a meter. A centimeter is 100 times smaller than a meter. Right. A millimeter is 1,000 times smaller. Then we get into a micro, which is 10 to the -6th, and a nano, which is 10 to the -9. So I do want you guys to have those memorized. Before we go there, let's see, is it? Check and see if they give us any additional stuff on that, because I may want to expand on that just a little bit for you guys. Yeah, it doesn't look like it. Okay, so we'll go over to our board here. All right. So one way that you can remember some of the sort of smaller, more used prefixes is a saying that goes, King Henry died before, whoops, let's put that E where it belongs, before drinking chocolate milk. Okay, King Henry died before drinking chocolate milk. So the before in the middle, this is your base unit. All right, so a base unit, again, can be something like a liter, a meter, second, a gram, a couple different options, a joule for energy. And then each of these represents a prefix. Okay, the ones to the left are our bigger prefixes. So this is a kilo or kilometer. Here is a hecto. Here is a deca. Here is a deci. Here's a centi. And then this is a milli. Oh, sorry. Milli. Okay, so 2 L's or 1 L? I don't even remember. I'll go with 1 I. Okay, so King Henry died before drinking chocolate milk. Now, this gets me just within the range of kilo and milli. It doesn't include the other guys outside of that. So let me go back to here. So just know that there are going to be ones that are smaller than that and ones that are bigger than that. When you think of a giga, like your brain probably goes to a gigabyte, that's exactly what it's talking about. It's that many bytes of information. So what I like about this is if it's written correctly, like you would write it in a book, is that you can use the decimal hopping method to convert between units. Hold on one sec. Let's see. What's the hecto? So that is a unit that we don't see very often. All right. So kilo, hecto, deca. It's just 10 times as big as the base unit. Or I'm sorry, 100 times as big, because this would be 10, this would be 100, this would be 1,000. So let's say that we're given 22.5 grams. Karl Marx gave the, there you go. All right, awesome. So we're starting here at our base unit, and we want to, let's say we're trying to find how many centimeters this is, because the problem requires you to do that. So I need to go from my base unit over to centimeters, which is the chocolate. So I'm gonna hop 1, 2 hops. Take your decimal, hop it out 1, 2, and fill it in with a 0. You end up getting 2250 centimeters. Okay. Another example, let's say we have, let's say somebody went running, they ran 18.3 kilometers. and I want to find how many, let's just find how many meters that is. Okay, we tend to convert a lot between meters and kilometers, or grams and kilograms, things like that. So you start with your given, where over here at King, we want to go to M, which is here, our base unit. So we have to hop 1, 2, 3 hops. So I take my decimal and I hop in the same direction that you're hopping up on the diagram. 1, 2, 3. Fill in with zeros, we get 18,300 meters. This works going in the other direction as well. So if we're going from something that is smaller to something that is bigger. So let's say I have 41,200 centimeters. And I want to know what that is in reference to a kilometer. Okay. Well, I start at centimeter over here. I need to get to kilo or kilometer over here. So I've got to take 1, go through the base unit, 2, 3, 4, 5 hops. And in this case, I'm taking 5 hops to the left. Where my decimal lives on this number is right here. So we're going to hop 1, 2, 3, 4, 5. We end up finding out that 0.412 kilometers is the same thing as 41,200 centimeters. All right, and there are a couple other ways to solve that, but I just always found that one to be useful when you're trying to go through between like centimeters and meters and kilometers. All right, questions on King Henry died before drinking chocolate milk? Obviously, there's the other ones outside of that that I want you to know as well. Okay. Let's go back to our slides. So if you notice, all of these prefixes are in some base 10. So you don't have to remember like, oh, well, when I'm going from a teeny thing to a bigger thing, like some inches to feet, that's a factor of 12. If I'm going from feet to yards, it's a factor of 3. If I'm going from feet to miles, it's 5,280. You just know that it's all a base 10, right? It's going to be a multiplier or divider of some 10 value. We have a unit for our volume, which is the liter. So we use gallons, but again, a gallon versus a quart, it's all messy. Whereas a liter or a milliliter, those are directly related to each other by a factor of 1,000, right? Because a milliliter is 1,000th of a liter. King Henry died before drinking chocolate milk. The before, which is our base liter, and the milk is 3 hops or 3 zeros. So there's some other ways that we can talk about volume. Over here, you can see that 1 milliliter is equal to 1 centimeter cubed. So we use that, that one quite a bit. So just know that if I'm saying a milliliter and the problem's asking you for something in centimeter cubed, it's a real easy one-to-one conversion. Another thing, a decimeter cubed is equal to a liter. That one we don't see quite as much, but this one is definitely something we use a lot. If you've heard of like a cc, like give the patient 65 cc's, that's what they're talking about. So when we're measuring values in science, really in anything, there's a certain level of uncertainty that we have to our measurements. Different measuring devices have different levels of accuracy or degrees of accuracy. So if I look over here at this graduated cylinder, it has markings at every 10 milliliters, and it has some smaller ticks in between. This syringe doesn't have anything labeled on it, so I don't know what I'm supposed to do with that. This guy is pretty precise here. If we look, he has bigger lines at every milliliter, and then he has tick marks in between. So this guy has a higher level of precision than this guy. If we look at the volumetric flask, usually it just has a line right here that'll say something like 1 liter. That has very, very little precision to it. Obviously in science, we want to be as precise as we can, but we don't want it to become so cumbersome with that precision that we can't like actually run the experiment. So sometimes you have to have a little bit of guesstimation in there. Temperature. So by definition, temperature is a measure of the average kinetic energy of the particles in a sample. So when we're talking about temperature, what we're measuring is pretty much how quickly the particles are moving within that substance. If they're moving very fast, we have a high kinetic energy, we have a higher temperature. If they're moving a little bit slower, we're gonna have a lower kinetic energy or a lower temperature. So when I stick that thermometer in room temperature water, the water particles are pinging it enough to raise the temperature, but not as much as say if I took that thermometer and I put it in like boiling water, those water particles are gonna be hitting that thermometer really, really hard. It's gonna bump the temperature up. So in scientific measurements, Celsius and Kelvin scales are most often used. We tend to stay away from Fahrenheit. Why do I like Celsius? Why do we like Celsius? 100-degree intervals in reference to water's boiling and freezing. So at 0 degrees Celsius, water will freeze. At 100 degrees Celsius, water will boil. You do need to know that. The numbers are a little more strange when we're dealing with Fahrenheit, right? 32 degrees Fahrenheit is when water freezes, and 212 degrees Fahrenheit is when water boils. And those numbers are sort of random, and it's a 180-degree interval scale. We don't like that. Over here we have Kelvin. Kelvin is also an 100-degree interval as far as boiling for water. The only difference between Celsius and Kelvin is whatever number you have for your Celsius, you're just simply going to add 273. Okay, so if you're at 0 degrees Celsius, you just add 273, you'll get 273 degrees Kelvin. If you're at 100 degrees Celsius, you'd add 273, that'll give you the 373. All right, so pretty quick conversion back and forth. The conversion between these two is a little more of a pain. So the Celsius scale is based on water properties. Again, as far as our SI units are concerned, Kelvin is the base unit for the SI system. It has a lot to do with properties of gases, mainly that when you get towards absolute zero, you'll never cross absolute zero, or you'll never get into a negative Kelvin value. Because if you had a negative Kelvin value, it would mean that the motion of the gas particles cease to exist, and you move into something that is the opposite of motion. And I'm not talking about non-motion, I'm talking something even beyond that, which is not possible in our existence here. So super easy, just add 273 to get to your Kelvin. Your Kelvin value should always be the bigger number of the two. Fahrenheit scale is not used with science. This is one of the equations to convert between Fahrenheit and Celsius. You may have to do this conversion in homework and on exams, but traditionally in science, we don't see Fahrenheit. Here's the equation if you're given Celsius and for whatever reason you want to calculate Fahrenheit. So let's say that somebody from Europe said, oh, it's 37 degrees outside. And you're like, it's super warm outside. What are you talking about? How is it 37 degrees? Well, you got to convert that to Fahrenheit. That'll get you into the temperature that maybe is better for your frame of reference. All right. So one property that we have, a physical property of material, is known as density. Density is a derived unit of measurement. When I say derived unit, that means that it's made up of other units, okay? So Density will always equal mass over volume. So if you ever want to solve for density of something, you have to have two measured values. You need to have the mass and the volume. Let's get out of here for a second and try some density stuff. Go into that in a minute. So density equals mass over volume. There are three variables in this equation. So you would always be given two of the variables and have to solve for the third. I could give you mass and volume and I want you to find density. I could give you density and have you find mass, or I could give you density and mass and have you find volume, or vice versa. So some units that you'll see for density: grams per centimeter cubed is one we see a lot. So gram is a value of mass. Centimeter cubed is some sort of volume. Another unit, there's a bunch of different ones, but just to get sort of comfortable, grams per milliliter. You could see something like kilograms per liter, right? Kilogram is a mass value. It just has a prefix stuck on it. And underneath it, we have a liter. These are all different options, all right? There are many, many more out there. So just get used to, if you're seeing a unit stuck at the end of a number that has like two values and one's a mass and one's a volume, it's talking about density. Okay. So let's do a problem. What is the density of a substance? Density of a substance that has a mass of 32.8 grams and takes up 15 milliliters. Okay, so what is the density of a substance that has a mass of 32.9 grams and takes up 15 milliliters? You don't have to put it in the comments or anything. We'll go over it in about 2 minutes. How many decimal points do you want? I will talk to you guys about that in a little bit when we go over significant figures. I'll let you know. Okay, so I want you to start getting in the habit when you're working on these word problems to sort of follow a consistent process of writing out the given information and then writing out explicitly what you're trying to find. So in this problem, so you'll see me set things up the same way. I'll write my given and what I'm trying to find. And it may seem sort of simple or silly right now, but as problems get more complicated, I just find that it helps. Like word problems, a lot of times my students know how to do the problem, they just don't know how to pull the information from the word problem. So with our given information here, I have two pieces of information. One of them is the mass, because it literally says mass. So we say mass equals 32.9 grams, and it takes up 15 milliliters. So it doesn't explicitly say here that the volume is 15 milliliters, but you want to start getting used to seeing things takes up a certain amount of space. That's going to be a volume thing. Milliliter is a measurement of volume. So I know my volume for this is 15 milliliters. The problem tells you right at the top what is the density. So I want to go ahead and find my density. We know that density equals our mass over our volume. It doesn't say anything about wanting it in specific units, so you can just go with the units that are there, which is grams per milliliter. So we can actually just plug our stuff in directly, and we get 32.9 grams for every 15 milliliters. The gram and the milliliter will not cancel with each other because they're different units. So you have to keep both of them at the end. So when you plug this into your calculator, you should have gotten a number with a pretty long remainder on it. So it's 2.19333, so on, so on, and so on. Always pair this with a unit, gram per milliliter. Okay, don't leave the unit off. Now, because this has 3 significant figures and this has only 2 significant figures, I'm going to go with the 2 sig figs to honor at the end. And we'll talk about sig figs in a little bit. So 2.2. Why? Because I'm going to keep this 2. That's significant. The 1 is significant, and I round off using the 9. The 9 tells the 1 to go up to 2. So 2.2 grams per milliliter. All right, I'm going to give you another one, structured in a little bit of a different way. So, how much space does 15 grams of a metal with how much space does 15 grams of a metal with a density of 3.89 grams per milliliter take up? Okay. So how much space does 15 grams of a metal with a density of 3.89 grams per milliliter take up? I'll give you all about 2 minutes on that one as well. Okay, so in this problem, how much space does 15 grams of a metal with a density of 3.89 grams per milliliter take up? So I'm going to write out my given information. I know the density, it says it right there, equals 3.89 grams per milliliter. How much space, that's talking about volume, does 15 grams? The unit of gram is talking about mass. So you're just going to have to start getting comfortable with gram meaning mass, liter meaning volume, things like that. So I know the mass is equal to 15 grams. We're trying to find the volume. Okay. So density equals mass over volume. Some people like to plug their information in first and then isolate the variable that way. I'm going to isolate for volume beforehand. So volume is below the fraction bar here, which I don't like. So I'm going to multiply this side by volume and this side by volume. The volumes will cancel there. And now I have a new equation that says volume times density equals mass. But I want volume by itself, so I'm going to get rid of density. I'm going to divide density on this side, and I'm going to divide by density on this side, and that just made a triangle, ignore that. And what I end up getting is that volume equals mass divided by density. So you guys will be required to do some mild isolating of variables. So if you have to refresh on that, go ahead and do so. All right, so I know that my volume is going to equal my mass over my density. Here's my mass. The problem doesn't, again, explicitly say what units it wants it in, so you can just roll with whatever comes out. Mass is 15 grams over 3.89 grams per milliliter. I like to write all my units. Within these problems because it kind of gives me confirmation if I've solved them correctly. So looking here, gram is above the fraction bar here, and it's below this fraction bar. So I'm going to cancel those two out. Milliliter is below a fraction bar and below another fraction bar, which actually puts it back up on top. So the unit that we're now left with is a unit of milliliter, which totally makes sense for volume. As far as what the numerical answer is, we take 15 divided by the 3.89, and we get this long number, 3.856041111. I have two sig figs here, so I'm going to go with 3.9 milliliters. Any questions on that? On that equation, on plugging stuff in, on where units are coming from? So on your first test, you'll definitely have like some density questions, stuff like this, and then density will just sort of become second nature as we move through the semester. So being able to move from density to volume or volume and mass to density, whatever. Great. So uncertainty in measurement. So whenever you're taking a measurement, there is a certain amount of uncertainty based off of you as a measurer and the equipment that you're using. How precise, so someone had asked how many decimals do you want us to use? And I said, oh, I'm gonna go off of significant figures. Well, what are significant figures? Significant figures pretty much tell you how precise or imprecise a number is. So if you've got a number that has a lot of precision to it, you would expect to see a lot of significant figures. If the number is kind of crappy, you're only gonna have, you know, one or two significant figures. So the term significant figures refers to the digits that were measured. When rounding or calculating numbers, we pay no attention to significant figures. So we do not overstate the accuracy of our answer. Or sorry, we pay attention. when we're rounding calculated numbers, we pay attention to the significant figures so we don't overestimate the accuracy. So when we were calculating this here, okay, my calculator spewed out this answer of originally, which was 3.85604, so on, so on, so on. So it looks like, or it appears that we have like a really precise answer, and you're like, oh man, my volume measurement is awesome. But if we look back at our given data, this is sort of a crappy piece of information. 15 grams is not like a really precise measurement. It's, you know, is it 15 grams, 16 grams? Like, why didn't you say 15.196? You know, they didn't, whatever their equipment was, wasn't very precise. This density is also not super precise either. So your final answer or your calculation can really only be as precise as your least precise piece of information, or you're only as strong as your weakest link as far as your given information. All right, so let's talk about significant figures and what we classify as significant figures, because when you're rounding, you've got to know if the numbers you're looking at are significant or not and things like that. So easiest rule is the first one. All non-zero digits are significant. So I'm going to write just a number on the side here. 3652. Okay, 3,652. I would say that this thing has 4 sig figs. 4 sig figs. Why? Because all of these are non-zero numbers. Those are easy to calculate out. It gets more difficult when you have zeros. Zeros are the things that give us trouble on determining significance. So the next rule about sig figs is that any zeros between 2 significant figures are themselves significant. So when you're looking at a number and its precision, we can't have a number that's like precise and then it's not precise and then all of a sudden it's precise again. Like it's a chunk of precision. So when I have a number, or put a number in here, let's do 1, 0, 0, 0, 0, 1. Okay. So 100,001. So when you're writing that number, you're not just saying loosely like, oh, I don't know, it's 100,000 people. It's like, no, you counted 100,001 people, like to the T. We know that this is significant, and we know that this is significant because of rule 1, all non-zero digits are significant. The zeros in the center have to be significant. You can't, again, have something that's significant and precise, and then all of a sudden you drop off significance, and then you hop back on the significance train. Doesn't work that way. So every one of these would be significant. So I would say that this thing has 6 sig figs, or 6 significant figures. Okay, any questions on those first 2 rules? No. Okay. Zeros at the beginning of the root number are never significant. They're just acting as a placeholder. All right, precision, numbers become more precise as we add stuff this way, not as we put stuff in front this way. So let's write out an example of this. So 0.0000205. If I was trying to figure out how many significant figures this has, I would find my base number first. So this is the number itself, the 205. These zeros here are just acting as placeholders for the decimal. They're letting you know like how far away from the decimal you are, but they themselves don't talk about precision whatsoever. So this is significant, and this is significant because of rules 1 and 2. These guys here, including that one, are not significant because of the 3rd rule. So we would say 1, 2, and 3 sig figs. Next rule. Zeros at the end of a number are significant if a decimal point is written in the number. So if you're seeing a decimal and you're seeing zeros happen after the number, we are going to go with significant. Let's do an example of that. Okay. You know what? I'm going to write the same number a couple different ways. Okay. So I'm going to write 3, 3.0, and 3.000. Okay. In that first one, I'm just saying, yeah, it's like, you know, it's like 3. I don't know. Maybe we're talking about grams. Okay. It's 3 grams. So you may be looking and saying, well, aren't those all saying 3 grams? No, this is like casually saying 3 grams. I don't know. I'm somewhere between 2 and 4. I'm going to say 3 grams. Okay. So this thing has 1 sig fig. Really crappy, low accuracy number. Looking at this here, we've got 3.0. Anytime you see a decimal, if there's a 0 coming after your base number, we're going to count that as significant. So this is significant and this is significant. 2 sig figs. What about that one at the bottom? That's like an awesome 3 gram measurement. Like that scientist had the really bougie scale and he was like, no, it's not just 3, it's 3.000. Okay. I am accurate to the 10, hundreds, thousandths place on this. So we would say that this thing has 4 sig figs, okay, or 4 levels of precision. So obviously the lower number is better in science, but you know, you can't have an infinite number of sig figs when you're measuring things. At some point you've got to cut it off, right? So I'm gonna write another number for you guys. Two numbers, okay? So I'm gonna write 21,000 like this, and then I'm gonna write 21,000 like this. The only difference is that I put, boop, a little dot right there. What that dot tells you is that this scientist actually measured this value all the way to the ones. This one here is like, I don't know, it's 21,000 gallons, plus or minus. This one is like, no, it's exactly 21,000 gallons, okay? So this guy up here, these zeros, I don't know if they're significant. Sometimes we say they're ambiguous. So I'm gonna go with 2 sig figs for that top one. The bottom one though, on the other hand, we can include those zeros in the significance. So 1, 2, 3, 4, 5 sig figs. So anyone out there have a question about these rules as far as sig figs are concerned? You will have to know how to do sig figs and calculating with sig figs and stuff like that. So if you do have a question, just throw it out there.
This is kind of about the sig figs, but kind of not. So say when you're doing a conversion and the smallest number is like 1, can you only use one significant thing in your answer then?
If you have, yeah, if you've got a calculation, and we'll talk about that when taking sig figs and putting it into calculations. If you have 2 numbers and you're multiplying them together and one of them only has 1 sig fig, your final answer can only have 1 sig fig. It tends to drive some of my students crazy because they're like, but this number was so precise when it came out of the calculator. Yeah, but the number you plugged in wasn't a good number. It was a low precision number, so your final answer is low precision. Okay, cool. Let's see. Okay, how do you know how many sig figs to use? Zeros at the end of a decimal aren't sig figs unless there is a decimal at the end. Correct. Zeros at the end of a number are not significant unless you have that decimal. So when looking at this guy here, the 21,000, it is only the 2 and the 1 that are significant. The zeros, I don't know if they're significant or not. I can't tell from the way that that's written. The 21,000 with the decimal, those zeros now become significant. I know it seems kind of silly, like that something like that would make a difference, but it does. Okay. Let's see. How do you know how many sig figs to use? So we'll talk about that in reference to calculations. Let's get out of here. Okay, I'm gonna clear out these annotations.
All right, I have a question.
Yeah, Brittany, what's up?
So if we go back to that density example, the first one you gave us was 32.8 grams over 15 milliliters. And because 15 milliliters was only 2 sig figs, we rounded our answer to 2.2.
Exactly.
So what if it was 10 milliliters?
If it was written as 10 milliliters?
Yeah, but it wasn't written as 10.
So it was written, so it depends on how it was written, okay? So
Okay.
if I wrote it as 10 milliliters or 10 milliliters, okay? If I wrote it in this way, we would honor 2 sig figs. If I wrote it this way, how many sig figs do you think I can honor?
Just
one. So your answer has to go to 2 grams per milliliter.
Okay.
And I know that's like really frustrating. It's like, oh man. So that's why, you know, we're always striving to have like really good information that we're plugging into our calculations. But yes, when you're doing multiplication and division, you are only allowed to use the lowest number of significant figures for whatever your values are. We'll do a little bit of practice on that. Okay, so let's go back here. So looking at this number here, how many significant figures are there in this measured unit? 0.082060. Just give you 20 seconds. So you don't have to put the answers in the chat. Well, yeah, everyone's like, I got it, I got it. We'll go over it in a second here. Okay, so when looking at this, we've got a number that has a bunch of zeros in a bunch of different places. So I want to find my base number. So my base number is this sort of thing here. Obviously the 8, the 2, and the 6 are significant because they're non-zero. This 0, real easy, is significant because you can't be precise, imprecise, then precise. It's a chain of precision. We know that zeros that sit in the front of our base number are not significant. Those are just placeholders. They're just letting us know how big or small it is in reference to the decimal. This 0 over here comes after the decimal, and it comes after the base number. So we're going to say that that's also significant. So 1, 2, 3, 4, and 5. All right. Why is this 0 significant? Well, scientists are lazy people. They don't want to write numbers if they don't have to. So if they didn't need the 0, they just wouldn't have included it. They would have just written it without this thing here. All right. They would have written 0.08206 if they only needed 4 sig figs. But for whatever reason, the equipment they had gave them a value all the way out. So we include the 0 there. All right. Okay, so here's an exercise determining the number of significant figures in a measurement. So how many significant figures are in each of the following numbers? Assume that each number is a measured quantity. So A, B, and C. So try and decide how many significant figures you think each of those would have. Guy, I like your dog. All right, so looking at these, A, all of those values are significant. The 4 and the 3 are, and we fill in the center. So this thing is 4 sig figs. This second number is written in scientific notation. I'm going to write it over here, 6.023 times 10 to the 23rd. The times 10 to the 23rd just means it's a really big number, and we would hop that out 23 hops and fill it with zeros. In scientific notation, any of the values that are included in the first part are significant, okay? So this is significant, this is significant, this and this. So this would be 4 sig figs. C, that's a real guesstimated number, 5,000. So this is significant. Those zeros don't have any sort of significance to them. So we're gonna go with 1 sig fig. We don't like that. We like to avoid 1 sig figs as best we can. But that's just how it goes for this one. Okay. So when we're running calculations, and really for this class, we tend to just do mostly addition, subtraction, multiplication, division. Every now and then we do some exponent and log stuff. But for addition and subtraction, answers will always be rounded to the least significant decimal place. So whichever of your 2 starting numbers has the lowest number of decimal places, that's how many decimal places you have to honor for your final answer. It's a little bit different for multiplication and division. When you're doing multiplication and division, answers are rounded to whichever digit has the least number of significant figures. So if I have a calculation that has 15 sig figs, or rather a piece of data that has 15 sig figs and another one that has 2 sig figs, unfortunately, my final answer will only be able to honor the 2 significant figures. So let's look at this one here. I've got 3.0, or rather 6.03 grams plus 7.1 grams. It may be helpful for you to write this out like old school, like 3rd grade style. So you take the 6.03 and you stack it over the 7.1 and you line up your decimals. Remember when we used to do that? Because it makes it really clear which one has more decimal places. This has excess decimal places. So I know I'm going to need to truncate my final number off there. So when I plug this into my calculator, I end up with a number of 13.13. Okay. I can, in addition, subtraction, only honor the lower decimal place. So I can only have 1 decimal place. That means that the 3 has to get dropped. So this is where rounding comes in. So you take the number that's getting dropped, it will either tell the next number that's staying to go up or to stay in place. If we're 5 and up, we round up. If we're 4 and 0, we stay in place. So this final answer would end up being 13.1 grams.
I have a question.
Mm-hmm.
What if there wasn't a 0.1? Do you have to put a 0.0 to equal it out? Like, what if it was just 13?
Yes. So if your final answer ended up being like a whole number, you would have to fill it in with a 0. Mm-hmm. So let's say I had, let's say we're taking 2.7 and we're adding it to 3.3. Okay. This would be a 0 and this would be a 6. We would keep the 0 in that place to show that we are in fact significant out to 1 decimal place. Okay, so here we've got a division problem. So we're going to take those same numbers or similar numbers, take 6.03 grams, and we're going to divide it by 7.1 milliliters. And we want to come up with a final answer that is correctly rounded. So all of those numbers that are there are like sort of correct, but they're not rounded to the correct accuracy. So go ahead and make that happen. Okay, so the calculation itself is pretty simple. I mean, you have a calculator, so you can plug it in. And we end up with a number with a bunch of trailing decimal values, so 0.84929577, whatever, it keeps going. So I want to round to the correct number of sig figs. Multiplication, division, honor the lowest sig figs. This thing here has 1, 2, 3 sig figs. This thing here has 2 sig figs, so my answer can only have 2 significant figures. So this is the sort of extended answer. This is the correct answer, rounded. We want to keep the 8. We want to keep the 4. We cut everything else off. The 9 tells the 4 to go up to be a 5. So any questions on that as far as multiplication division is concerned? Don't use the addition subtraction for multiplication division and vice versa. You want to keep those separate. All right, I think we're going to stop there for today. So if you have any additional questions, feel free to stay around and I will put you in the waiting room and chat with you. My people who have quote unquote lab today, Susan sent you guys an email, hopefully that you got, that had her contact information that again, just sort of reiterated, lab is done on your own time. If you want to talk with her, email her, meet her, she will be available at 2, okay? So otherwise, have a really good weekend. Make sure you're getting into mastering chemistry, make sure you're looking at labs and things like that and getting into the syllabus and confirm that for me, all right? Otherwise, I will see you guys on Tuesday. All right, bye.
Hello.
Hey, give me just a second, people who are hanging around, okay? I'm gonna put you into a waiting room so that we can chat in private. Let me just end this recording.